Hi everybody, this is the video number 1 for the lab number 3. We will repeat an experiment that led to Thomson to become Lord Thomson. He has measured U/M ratio. So what we have here is a vacuum tube, and we can generate some electrons and accelerate those electrons using so-called electron gun, which is located here. Well, I can turn on the power supply and you can see the light. So there's a heating element and electrons being ejected from that filament, and here we have two other electrodes, positive, the red one, and negative. And if we apply a high voltage here in this region, strong electric field will make electron accelerate, and then they will travel along this fluorescent paper. Those blue lines, not electrons, of course, we cannot see electrons. This is just a fluorescent track on the paper where electrons travel through this paper. And here we can read the accelerating voltage. Let's set it to 4,000 volts. 4,000 volts, 4 kilovolts. Well, in order to see the beam better, let's dim it a little. I can have a magnet here, and what is happening when I bring a magnet close, the beam is deflected. What do I know about magnet? Red means north. So north, very cold, magnetic field lines leaving the north. So magnetic field lines point outside like this, and the velocity of the electrons from the gun outside to the left. And we can use the right hand rule to see what's going to happen if I bring this magnet with the north pole facing the beam closer to the beam. You see the deflection. And my right hand rule says, okay, velocity points as a finger to the right, magnetic field line is supposed to point into the screen, and the force should deflect charges down, but they deflected up. Why? Well, because at the right hand rule it works for positive charges. For negative charges, what do we do? We flip it, or we use the left hand. Left hand tells me for negative charges, for electrons, deflecting force points up. That's why they point up. Well, what we will not use a permanent magnet for this experiment. It's not very reliable. We will use these coils. If I turn on the power supply, yes, and the current meter, ammeter, I can use this knob to provide some electric current through the coils. That electric current generates a more or less uniform magnetic field, and we can see how that field will affect bad junction somewhere. Did I turn it on? Okay, I did. Alright. So electric current increases. It's hard to read it here, but you can read it on this device. 104 milliamps. And I can increase or decrease electric current, and I can make the bending more or less. And by the way, now electric current bends down, what does it mean? It means that magnetic field now acts not in that direction, but in opposite direction at you. And well, now I can manipulate with the current and make it travel through a convenient location. A convenient location which I can easily read, like this one. So the x coordinate is equal to 9 and the y coordinate is equal to 2. Those are magnitudes. 9 and 2 for the point where the beam crosses the intersection. X equals 9, y equals 2 down, and the electric current is 232 milliamps. 232 milliamps. And again, the accelerating voltage is equal to 4 kilovolts, 4,000 volts. Okay. Now what I do? I want to flip the direction of a current. It's easy. I just flip the wires. I can turn it back on. And you can see the beam. The beam now doesn't go through exactly opposite location, but close enough. You can see the current travels in opposite direction. That means the magnetic field now points opposite to previous direction. So previously it was out, now it is in. Again, how do I know? I can apply, because I know those are electrons, I can apply again the left-hand rule: velocity, force, magnetic field away from you into this paper. But I want this beam to travel through this symmetrical, the opposite point, 9, 2 above. So I need to change the current a little bit, make an adjustment, make it a little bit stronger. Done. So now you can write down the values. Again, x equals 9 and y equals 2, but up. And the strength of electric current is 289, let's say 289 milliamps. 289 milliamps. And this is the end of the first video.